This is Outperforming Imperative with Pure Functional Languages. I'm Richard Feldman. So for the past couple of years, I've been working on building a programming language called Rock. And Rock is inspired by and a direct descendant of what has been my favorite programming language for several years now, which is Elm. Elm is one of the things that I love about it is it's got this really delightful user experience. It really gives me joy to program in it. It's a pure functional language, and it's compiled to JavaScript, so it's really good for making browser-based UIs. But I've wanted sort of like an Elm-like experience in other domains besides browser-based UIs. And so Rock has similar goals to Elm of having like a delightful user experience, and it's a pure functional programming language like Elm, but it's compiled to binary. So it's sort of for other use cases that Elm is not meant for at the moment. So I first got into Elm based on this blog post, Blazing Fast HTML in Elm, which came out in 2014. And one of the things that I appreciated about Elm was I had a relatively performance-sensitive UI that I was building, and I really liked to see this benchmark that sort of gave me confidence that I was going to have a fast experience when I was building my apps in Elm, and I wasn't going to have a nice experience building it and then have things run slowly when I got done. So I want to sort of keep that value in Rock. Like, it's really important to me that, like, hey, let's go fast. Let's build a programming language that runs programs really fast. Of course, the trouble with that is that this is a pure functional programming language, and pure functional programming languages are all about pure functions, as in like every function is pure. And that means no side effects and no mutation, which can be a bit of a challenge when it comes to performance if you're trying to go really fast, because the fact of the matter is some algorithms just require in-place mutation to run fast. Like, for example, how competitive could a pure functional language possibly be at a mutation-heavy algorithm like quicksort? This seems like somewhat of an intractable, unavoidable downside. So, fortunately, though, there are several different considerations to performance, like, for example, the language overhead. Like, how much overhead does the language introduce? Sort of how close can it get you to what the hardware is capable of? And that can be sort of balanced against, there's no side effects, there's no mutation. So when you put all those things together, how well can we come out when compared to imperative languages? Well, let's kind of look through these and just talk through them. So first, we're going to talk about language overhead, like in general and also as it pertains to Rock. So Haskell is a very well-known, probably the most well-known pure functional programming language. And we actually use it at work where I work at No Red Ink. So our backend for many years was Ruby on Rails, which is a pretty common tech stack. And then in recent years, we've actually been migrating our backend from Ruby to Haskell. And so in particular, we migrated one of our services, actually our most high-traffic, performance-critical service, to Haskell. This is serving billions of questions every year. We make software for English teachers, so students are answering billions of questions on our site, all going through this Haskell service. And what we found was that when we migrated this from Ruby and Rails to Haskell and service, basically doing the same job as it was doing before, it's slightly different, but not really that meaningful from a performance perspective, the delta was quite large in terms of performance. It was about 10x faster. Now this, we're well aware, was not because like pure functional programming is like, oh, it's this magic sauce that just makes everything run faster. No, it definitely wasn't that. It's just because some imperative versus pure functional, but they just sort of dominated in this case, which led to Haskell being a lot more performant in practice than Ruby was. So let's talk about that execution model a little bit. I mentioned that Ruby's interpreted. There's quite a few languages that will do interpreted, basically like interpreting the source code, parsing it into an AST, and then interpreting that on the fly. So Python, Ruby, JavaScript all do this. May or may not have JIT, which is a just-in-time compilation, which can speed that up in like really tight loops, things like that. Some languages do interpreted bytecode, so like Java, C#, Elixir, compiling to Beam bytecode. Other languages go straight to a binary, like just an individual standalone binary. So Go does this, Swift does this, Haskell also does this. These are generally the fastest category of things. Like these are pretty much sorted from sort of highest overhead to least overhead. But there's something that's worth calling out as almost a different category unto its own, which is LLVM compiled to binary. So LLVM is basically a library that's for optimizing compiled binaries. It's not like LLVM is like the only way to get this extra speed bump, but languages like C++ and Rust and Zig all use this to get like really, really exceptionally great performance out of their binaries. And of course, that's what we want for Rock too, so that's what we've been using. I mentioned boxing, so boxing basically referring to things being allocated on the heap, which generally is a lot slower than allocating them on the stack or in registers. Some things that can be boxed include numbers, so like in Python, numbers are boxed, for example. That means that doing number stuff in Python is generally a lot slower, and why you have libraries like NumPy and stuff to speed that back up. Objects and records also very commonly boxed depending on the language. Functions and closures also potentially boxed depending on the language. Basically, that's just sort of another source of potential slowness. Memory management, lots of different memory management strategies. A really common one, that's sort of the old school way, was like individual allocations and deallocations, like C, C++, Rust, and Zig. These languages will help you out with this. They're not going to make you do it by hand like you had to in C, like every single allocation is specifically called malloc and then called free again. But at the end of the day, like that is how the memory is being managed. It's sort of like one allocation at a time. Then you also have tracing garbage collectors, which is a very, very popular strategy these days. So like Go, JavaScript, Haskell, also like Java, and the list goes on for tracing GCs. Big downside of tracing garbage collectors compared to individual allocations and deallocations is that you get garbage collection pauses. So this is all something that we're probably familiar with. The program just locks up for some period of time while it's doing this garbage collection. There's another memory management strategy that does not have garbage collection pauses, which is quite nice, which is automatic reference counting. So Python, Swift, and Rock all do this, and the usual downside there is just that the reference counting sort of has more overall overhead typically, so that sort of the throughput is less compared to tracing garbage collector, even though you don't have the GC pauses. One of the things that you can do to sort of reduce that downside and make it so that it has higher throughput without reintroducing GC pauses is what's known as static reference counting. I know that Swift does this in some form, but I'm not a Swift programmer, not sure exactly how it works. But I know that what we did in Rock to do this was there were these two papers that we implemented. One is called Counting Immutable Beans, the other is called Perseus. And basically these are two ways of, among other things, optimizing it so that you don't need to do as many reference checks at runtime, as many reference count operations at runtime, because we're able to sort of detect at compile time where they would be happening and cancel each other out, and we can just kind of throw them away. One other thing I want to note, I don't have time to get all the way into it for this talk, but there's another thing that Rock does that's pretty novel in terms of memory management. The upshot of it is that instead of using automatic reference counting, you can completely transparently to the application author in some situations do arena allocation, bump allocation, which are just way faster than any of these other strategies, including tracing GC, including even like individual allocations and deallocations. I gave a whole talk about this, so if you're curious about that, you can check it out later. But suffice it to say, this is one of the things that I think is going to be most promising for Rock's long-term memory management, even though for the rest of this talk I'm not going to be using it. Okay, so to sum up, when it comes to language overhead, we've basically tried to do as good of a job as we can of minimizing the language overhead of Rock. So we're using LLVM, that's like basically sort of the gold standard for high performance compiling to binaries today. We're using unboxed values basically everywhere we possibly can. There aren't any values that I know of that are boxed unnecessarily. And when it comes to memory management, we're doing static reference counting along with some more exotic stuff like arena allocation behind the scenes. So overall, I'm like feeling pretty good about this. Like, okay, I think we're doing a good job here. Good start, but that was sort of the upside section, right? Now we have these two things that we have to deal with, which is we're not allowed to do side effects and we're not allowed to do mutation. So how do we compete when those are our restrictions? So let's talk about the no side effects thing. Well, fortunately of the two, this one turns out to not be as big of a deal as you might guess. A common question that I hear asked of people who talk about pure functional programming languages is, are you just heating the CPU up? Side effects are like everything, so I mean, like, what are you doing? If Haskell doesn't do side effects, like how is most of our production traffic running on Haskell? Is it just like not doing any effects? Is it never talking to database? No, of course not. It's doing all those effects. They're just not side effects. They're still effects, but they are now managed effects. So side effects versus managed effects, that's really the trade-off we're talking about here when it comes to performance. Here's an example of something that does side effects. This is JavaScript using promises. So we're setting promise 1 equals fetch some URL. Promise 2 is fetch the URL dot then, and then there's some callback which is going to return another promise. You could chain these together, et cetera, et cetera. Promises are a super common thing in JavaScript. They're nice for modeling asynchronous tasks that can sort of be chained together, and it's something that is done all over the imperative world. Managed effects, now hold on because this is going to look extremely different. As you can see, this is super different and weird and alien. No, it's the same thing. It's basically just promises. The only difference is like this is an Elm syntax, so it's a little bit different. Instead of a dot then, you have a pipe to and then, but same basic thing. So if you ever look at a large pure functional program, structurally it's very, very similar to promises. The only difference is that with promises, right when you instantiate the promise, it runs the effect. Like as soon as you call fetch, boom, it does the HTTP request right then and there. Whereas with managed effects, it's basically you're building up the same structure, but it doesn't get executed right away. Instead, you build up this big sort of chain together task, you hand that off to main, and then the language runtime will actually execute that when you start the program. That's the only difference. So it's nothing mysterious. It doesn't feel like a totally different way of doing effects. It's just like kind of like promises, but you do that everywhere. Now, one important difference when it comes to performance is that you do have to do this for all effects. So in a language that supports side effects, you don't have to have promise for everything. Sometimes you can just have a normal function call that does side effects. Whereas in a language with managed effects, every single effect is done in this way with sort of this like promise-like wrapper. So really, kind of the question comes down to, what is that overhead? Like if we have to have this sort of wrapper around all of our effects, like promise or task, whatever the case may be, how significant of an overhead is that for the language? So basically what it boils down to is that for both promise and task, they're essentially closures, that is to say functions that can sort of capture the enclosing scope a little bit, and they have other closures inside. That's really all there is to it. They're basically just closures, which is to say that the overhead of wrapped effects is pretty much just whatever the cost of closures is in your particular language. Now, the thing is, that overhead can vary pretty dramatically. Like I mentioned earlier, one of the things that can be potentially boxed, which is to say heap allocated, which is to say taking a lot longer than things that aren't boxed, are functions or closures. Fortunately, in the case of Rock, we were able to do this. We don't box them. This is one of the many things that we don't box. There's a whole topic of defunctionalization and how we're able to do that with direct calls instead of function pointers, which is really cool, but not the subject of this talk. So to sum up, in terms of managed effects and the overhead that they have on the language, task itself is unboxed. The unboxed task is essentially just a bunch of closures inside other closures, which are also unboxed. And we have these enumerated direct calls with defunctionalization, all of which basically means that the overhead of this, these like wrapped effects that we have to do everywhere, it's so minimal that it's honestly not something we're even worried about. Now, that's when it comes to no side effects, so small in terms of overhead that we're not worried about it. Different story when it comes to mutation. This is sort of the big one. Like this is like the big downside of pure functional programming, is that this makes performance optimization in some scenarios a lot harder. So let's just compare a mutation and non-mutation version of something to sort of get an idea for why this might be. So here is an imperative for loop. So we're saying let I equals 0, I is less than array.length, I plus plus, and then inside the body of the for loop, basically what we're doing is we're saying every element of this array, we're just going to double it right there in place. Pretty simple operation. Here's what it looks like if you don't have access to mutation. You're basically going to do a map, so array.map, and then this is also in JavaScript syntax, and then each element of the array, we're going to double it. Now this is going to make an entirely new array. So this sort of no mutation version is definitely not going to run as fast as the mutation version. Mutation is going to be a lot faster because it doesn't have to allocate an entirely new array and write all these values into this new array that's maybe not in your memory cache. Instead, it's able to do everything in place. Everything's going to probably be in the cache already. It's just going to go faster. So if you have this use case where you're like, that's what I need for performance, there's really no substitute for mutation in cases like this. Having said that, it's worth noting that there are some cases where actually making the new array can net become a performance optimization. So I mentioned that this was the benchmark that sort of got me into Elm in this blog post. And one of the things that it's comparing here is essentially how are these different frameworks and languages able to optimize rendering? And as it turns out, as you can see on this chart, like lower is better, so the smaller bars are running faster. All the ones at the bottom actually require immutability for rendering, and they're able to be much faster than the alternatives in large part because this enables a very quick comparison check between the old and the new state. And it's only able to do that because you're actually making a new one. If you were doing in-place mutation, in-place direct updates, this optimization would not work, and these things would be a lot slower in practice than they actually are. So basically, when the cost of immutability, which is a cost in this case, is less than the sort of like cost of rendering, it can actually end up working out to be a net performance improvement, which is exactly how these libraries and languages are able to win at this benchmark. As far as I know, the first person to come up with this observation that this could be used for performance optimization was David Nolan for ClojureScript, and then Evan Szaplicki, who made Elm, built on that to basically produce the results of that performance benchmark that I showed a second ago. Okay, now this is a case where, by coincidence, pure functional programming just happens to nicely work out to be a performance optimization, despite the fact that immutability is, all else being equal, a cost. But like I said earlier, some algorithms require in-place mutation to run fast. We cannot get away from this. There's just no substitute for it if we want to make them run fast. And I asked this question, like how competitive can a pure functional language be at a mutation-heavy algorithm like Quicksort? Okay, well, let's actually look at Quicksort itself. So I'm choosing this because it's a relatively well-known algorithm. Not that it's a thing that people are writing all the time, but we can kind of use it as a proxy for like mutation-heavy algorithms in general. So this is a very brief animation of how quicksort works. You definitely don't need to remember how all this works. But the important part is it's doing all these comparisons, and then at some point, this is the key, it does this swap. So it actually swaps in place inside the array those two elements, and again, there it's doing it again. So all of the other comparisons kind of could be fine in a pure functional sense. It's all relatively immutable, but that swap, there's just no substitute for doing that in place if you want quicksort to basically be quicksort and run fast. Okay, so here's an implementation of quicksort in JavaScript. It's actually just one part of it, the partitioning function. I just want to look at this real quick. We can kind of see all sorts of imperative stuff happening here, right? Here's a for loop. It's calling this swap function, which is swapping things in place. It's incrementing something, mutating that, doing another swap. There's just imperative stuff all over the place in this implementation. This is kind of like a textbook quicksort. This is not hand optimized. Like for all of the quicksort examples I'm going to talk through in this section, none of these are optimized at all. It's all just going to be like, take quicksort out of a textbook, implement it, done. Okay. So talking about quicksort in a pure functional language like Haskell, which we saw earlier, is capable on its own, just because the overhead is so much lower than something like Ruby, is capable of outperforming imperative languages at some tasks like we saw at work. But how does it do it quicksort? Well, one of the things that Haskell is known for is this very concise quicksort implementation. This is cool. It's neat that you can implement something that is quicksorty in this way, but a pretty reasonable objection to this is that this is in no way, shape, or form quicksort. So there's a whole blog post about this where it's basically like, yeah, the whole point of quicksort is that it's fast because of in-place mutation. This is just doing a bunch of cloning. It's not fast. It's not quick. So why are we considering this to be quicksort? Which I think is a valid criticism. But the blog post also goes on to say, okay, challenge accepted. Let's try to make one that does in-place mutation in Haskell. So that one is slightly less concise. Here it is. But beyond the conciseness delta, there's a much more concerning issue, which is that I'm just going to highlight a couple of function calls we have in here. Based on their names, you can guess why I might be concerned. Unsafe read, unsafe swap, and unsafe slice. Those don't sound safe based on the names. And indeed, if you look at the what they're actually doing, this is imperative Haskell. We are actually literally doing data.vector.generic.mutable, and we're in a pure functional language, or theoretically pure functional. We're actually doing like direct in-place mutation, and just hoping nobody notices. It's going to be fine. Everything's fine. So here's the docs for unsafe slice. It says like yield a part of the mutable vector without copying it, meaning if somebody else mutates it, it's going to mutate my copy, so referential transparency is now gone. No bounds checks are performed, so we're actually now less safe than something like Rust. We're in like C and C++ territory where we might get segmentation faults. If we try to read off the end of the array, we might get garbage memory, security problems. This function's all kinds of unsafe, so it's a good thing that they put unsafe in the title. I appreciate that. So this is kind of cheating. It's super cheating. Like we're just not doing functional programming anymore. But having said that, okay, fair enough. But how does it perform? Well, so I ran this against a number of other programming languages, and quick sorting 10 million numbers, and also running that 100 different times, and then sort of taking the average just so we can kind of see how things look, all done on the same machine. So JavaScript clocked in a little under 1.4 seconds. Haskell was actually slightly faster than JavaScript, which is impressive. Java was faster than Haskell, Go was faster than Java, and then C++, unsurprisingly, was the fastest. So this is all, again, just sort of textbook, unoptimized, just writing out quicksort according to the textbook, or in the Haskell case, doing this kind of weird unsafe thing. But it does show that it is possible for Haskell to beat these languages. But again, not by using functional programming. This is just by sort of cheating and doing really dangerous things that I don't think any Haskell would recommend that you do in production code unless there's really absolutely no other alternative. Having said that, it is good to know that if you need it, if you really need to do an imperative algorithm like that, you do have access to that in Haskell. Like you're not going to be blocked. You're not going to be like, oh, I guess we got to rewrite in C++. No, you actually can do it, and it can be competitive in performance with languages that are 100% imperative, that are imperative all the time, not just when you're sort of doing this carve out. The deltas that you see here, like the reason that some of these languages are different is basically that although there is the same algorithm behind the scenes, they're all doing asymptotically the same thing. There's different language overheads that are sort of accounting for these differences. Worth noting that in this benchmark, we found that tweaks affect the overhead a lot, so I really don't want anyone to look at that and be like, oh, Java is faster than JavaScript. No, this is not a reasonable conclusion to take away. For example, originally when we did this, we used Java array list, and then someone pointed out, hey, Java array is like much faster at something like this. Sure enough, that was true. That really brought things down for Java. We didn't consider that to be really a performance optimization because it's like either was a reasonable choice. JavaScript, originally we were sorting 64-bit integers, and even though JavaScript has a big num thing now, turns out it's just still way slower than double, which is sort of JavaScript's bread and butter. So go figure. We switched everything to double so as not to disadvantage JavaScript. And C++ is skipping bounds checks. Maybe that's unfair to the other language. That's definitely memory unsafe, but that is kind of idiomatic C++. So we figured, well, we're trying to just do a straightforward implementation here, so that seemed fair. Again, can't emphasize this enough. This is not a rigorous comparison. This is really just to talk about performance optimization in pure functional languages. Okay. Also worth noting that INTEROP is a much more common way to solve like uncommon performance problems like this. Like if I were writing Haskell and I found some algorithm that like really needed to be performance optimized, like it really needed that in-place mutation, I probably would not go into this like mutable, like let's just throw all our guarantees out the window land. Or if I have to, then I'm probably just going to do it by doing INTEROP with a much faster imperative language, like a low-level systems level language, C++, Rust, Zig, something like that. And this is what most languages do. I mentioned NumPy earlier in Python. The whole point of that is it just goes down and talks to like, I think NumPy is written in C, but basically a lower level language that's capable of running as fast as you need. Okay, but what if we could do it with optimizers instead? Instead of cheating, instead of like throwing all of our guarantees out the window, is there some way that we could optimize our way into getting that same level of performance? Because optimizers are pretty amazing things. Like the first optimizing compilers included Fortran, and apparently, so I'm told, people were actually surprised to find that the code written through the optimizing compiler actually ended up in practice being faster, typically, than code written by hand, like in assembly language. People were really surprised by this. There may come someday be a day where, much like with games like chess and now Go, humans are just incapable of beating optimizers. We're definitely not there yet, but it's theoretically possible that we could get there where you just can't really catch up, and also in the typical case, it's way faster to let the optimizer do it. So if we can, we would like to not have to resort to things like INTEROP or these secret mutation-y, unsafe things. So one example of a good optimization that's really common and important in functional languages is tail call optimization. This is something where we don't need to drop down into other languages. We don't need to do unsafe things. We can just let the compiler sort of translate pure functional code into code that is equivalent to the imperative counterpart. So basically any imperative loop, like a while or a for, or anything like that, can be expressed, there's a proof somewhere, I forget what it's called, as a recursive function instead. They're both like equivalent in terms of expressive power. The recursive function, by default, has very different runtime characteristics, but tail call optimization can detect when it's possible to optimize that into just the same thing. In other words, like the exact machine instructions that you get out the other side are going to be identical whether you wrote a while loop or you wrote a recursive function. So that's cool, and that's sort of promising. Could we do the same thing here? Could we make it so that we could take this imperative for loop where we did mutation in place for this array example and make it so that the array.map version optimizes to exactly the same thing, like same runtime characteristics? And the answer is yes, but you gotta be careful with that because if we're doing things in place, it's not really immutable anymore. Except it can be in one situation. Like if those compile to the same machine code and we happen to be in the situation where the thing that we're mapping over is never referenced again for the rest of the program, well, there's no downside. If it's never referenced again, yeah, we're mutating in place, but no one ever sees that. Like we're just reusing the same memory, and so it's still semantically immutable. We've still preserved all of our guarantees. Everything's still referentially transparent, but we're getting the runtime performance of imperative in-place mutation. Interesting, interesting. So this is the idea of opportunistic in-place mutation. Basically, the compiler figuring out when it's unobservable to change to in-place mutation and then just doing that, similar to tail call optimization. So this absolutely can be done automatically. One way to do it is by using reference counting, like we are using in Rock. So basically, the trick is just reference count counts how many times the thing is referenced. If you're about to do something that would ordinarily be an immutable clone, and you realize, wait a minute, the reference count is 1. That means nobody else is referencing it, so let's go ahead and do it in place. You can totally do that. This does mean that you need to be doing reference counting instead of a tracing garbage collector, because a tracing garbage collector doesn't have that information. It doesn't know how many references you have to something. So this optimization, when done in this way, sort of relies on that. As it turns out, very, very often, like a whole lot of the time though, you can actually do this statically. Like you can detect that the reference is going to be 1 at this exact point because you can see it's just never referenced for the rest of the program. So this is basically a way to detect many, but not quite all, but many, very many of these in-place mutation optimization opportunities at compile time. Now this means that you don't actually need to do the runtime reference count checks, which is good because it works with all of the different ways that Rock can manage memory, not just reference counting. And it also means that we can do it for unboxed values. So only boxed values are reference counted, and which means that if we're doing this static detection, we can do it for any kind of record, for example. This also reduces runtime overhead in general because it means we just don't need to do this extra comparison, this extra check at runtime to see if the reference count is 1. We just already know that it's safe to do it in place, and we can just remove that conditional altogether. The first version of this that we had going was made by Volkert de Vries as part of his master's thesis at Radboud University. Sorry, Dutch people, I know it's pronounced differently. But he used uniqueness types and inspired by the clean programming language. And this worked. This actually was able to do the in-place detection at compile time, but we found that it was kind of brittle, and it was actually like unfortunately easy to de-optimize it and like make a change somewhere in your program that caused the optimization to no longer be able to apply. So version 2, which is what we're using today, is based on alias analysis using the Morphic solver. This is a really cool library, especially academic folks. You should check this out. These UC Berkeley folks, they did this in undergrad. I played video games in undergrad. They made a static in-place mutation detection optimization library in Rust that's like pluggable into multiple compilers, one of which is the Rock compiler now. I guess the first of which is the Rock compiler. We've been sort of collaborating with them. So really appreciate all their hard work on this. It's really cool and really is helping out Rock to achieve its goals of performance. So if you're interested in that, here's some contact info to follow up with them. Cool. So putting all this together, we're talking about a lot of optimizations here and a lot of overhead reduction. How competitive can a pure functional language be at quicksort? So in terms of Rock, let's actually implement quicksort in a pure functional style, like not cheating, not resorting to imperative stuff. This is actually pure functional quicksort for real. So we saw in the JavaScript version, there was all these imperative stuff. There was like a for loop, and there was a swap in place, and partition index being incremented. But through the stuff we've just talked about, like tail call elimination, we can say, okay, we don't actually need to do a for loop. We can just do a recursive function. And instead of doing this swap in place, maybe we can just do a swap that's semantically immutable, but hopefully can get compiled to in-place mutation in practice. So here's what partition looks like in Rock. It is definitely longer than the imperative version, I'm not gonna lie. And it's also doing what appears to be a lot more work. Like instead of incrementing that thing with plus plus, we're actually returning a record that has like the new index +1. The list is doing a full swap, which is, semantically is immutable, returning a new list. We're returning another record here. We're calling this partition help function, which is a whole another function, which is also returning records and calling itself, so it's recursive. Really just like looking at these two side by side, it's clear that quicksort, this is not where functional programming shines. This is not where yeah, I can't wait to write quicksort in a pure functional style. It's going to be really beautiful and elegant and concise. No, this is actually pretty much a pathological algorithm for pure functional programming. It requires in-place mutation to be fast, and that's just not something that pure FP excels at. It's great at plenty of other things, but this is not it. This is we're really at the at the worst case scenario pretty much for pure functional programming. But we have this question, where we saw in the benchmark with Haskell using imperative stuff was able to, be competitive with these imperative languages, just because Haskell has pretty low overhead overall. In fact, it was even able to be slightly faster than JavaScript. Where does Rock end up when we're using no tricks, no secretly imperative stuff, no INTEROP, just pure functional programming and a bunch of optimizations? Turns out, really, really fast. So this is a pure functional programming language. It has no business being fast at quicksort. And yet, because of all these optimizations that we're doing and all the low overhead that we've really been careful to bake into the language, granted, like I said, this is a pretty silly benchmark, but it's real. I mean, this actually, we got it to be faster than JavaScript, Haskell using cheats, Java, Go, and basically everything but C++. Not gonna lie, we just got all of this working 2 days ago, and within an hour or two, we were like, okay, well, how do we close that gap with C++? that'll be another talk, hopefully. That'd be really cool. But yeah, I mean, basically, the way that we were able to do this was by just optimizations. Which to me is like very exciting. You know, it's fundamentally now we have the same algorithm in terms of asymptotics, and just that difference in overhead, we were able to sort of bring that down as low as possible, meant that, yeah, I mean, even for problems like this where you need in-place mutation to be fast, that's achievable now. Okay, so to sum up all the optimizations we sort of talked about here, we have the LLVM optimizer. This is doing all of our like really low-level stuff, same thing that C++ and Rust and them and Zig use. That's doing a lot of heavy lifting here for sure. Unboxed values really helps out the LLVM optimizer, just not doing these like heap allocations that we don't need to. Static reference counting, that was in use there, so that was all automatically memory managed code. We can do even better with other memory management strategies, but it seemed like for a fair comparison, we shouldn't use those here. Tail call optimization, absolutely essential for quicksort. We tried actually doing it without tail call optimization just to see what happens, and the answer is you just sit and watch the computer do nothing for a while, and then eventually it stack overflows. So don't recommend that, but fortunately, when you do have it, it's quite fast. And then finally, the real key that you know, without which this is just totally hopeless is the opportunistic in-place mutation. And that's one of the things that, as far as I know, Rock is the only functional programming language that's sort of aimed at being like a real used in industry language that's doing this. I think all the other languages that are doing it are like academic research languages. So we're excited to see what it can do. Okay, so let's summarize all the things we talked about. So first, you know, this is a language that comes directly from Elm. This is a direct descendant of Elm. I've had this really delightful experience using Elm. It's a pure functional language. It compiles to JavaScript. Really great for browser-based UIs, but I wanted to be able to do sort of other things than just browser-based UIs with a similar kind of feel of language. So those are all the goals of Rock. You know, delightful experience. I mean, I didn't talk about any of the experience stuff, but I've given some other talks on, you know, user experience and ergonomics of Rock. Pure functional, compiled binary, and yet we still want to go fast. You know, even though we're compiling to, you know, binaries and competing with all the other imperative languages that would do that, you know, we'd really like to be as fast or faster than sort of our contemporaries. There's three major performance considerations to this. So one is overall language overhead, and then there are these sort of drawbacks to try and work around, like we can't have side effects, can't have mutation. So talked about how, you know, overall language overhead can sometimes just dominate, and it doesn't, you know, those other considerations just don't matter. Like at work, you know, we are migrating from Ruby to Haskell. Most of our traffic now goes through Haskell, and we saw about a 10x improvement. By the way, we're hiring. If you're interested in working in technologies like Haskell and Elm, maybe someday Rock, who knows? And so what we saw is that we're able to sort of get language overhead for Rock as low as possible by using LLVM as our compilation backend, using unboxed values basically everywhere, and by doing memory management in these really low overhead ways with static reference counting, as well as these other novel things that I mentioned in other talks. We don't actually know, to be fair, like how well the static reference counting is going to work at scale, because Rock is a very work-in-progress language. It's like not really being used for anything serious yet. There are no sufficiently big Rock programs to say that, but so far we're feeling pretty good about the direction we're going. Talked about side effects versus managed effects. So Rock can't do side effects, but it does managed effects, which in practice feels about the same as using promises. The only difference is that, you know, you sort of have to use them everywhere for every possible effect. There is no like non-promise or non-task way of doing effects. So really that comes down to, okay, how efficient are those effects? And fortunately, when we're doing unboxed tasks, unboxed closures, and these enumerated direct calls, it turns out to be so fast that in practice we're just not worried about this being a significant source of overhead for the language. On the other hand, we talked about immutability. And so normally immutability is by default a cost, but we have seen use cases, some scenarios, where immutability at runtime, like actually, you know, creating new versions of values, can end up being a performance optimization depending on the libraries you're using and how quickly they can potentially skip doing other work. So this is a good example in the browser. But we also talked about how it's not always that convenient. Sometimes you have algorithms that require in-place mutation to run fast. And this is where this sort of long list of optimizations that we've got going on enables us to compete with those. All of this sort of culminating in our exciting result of actually being able to be faster at quicksort, which is pathologically hard and bad for pure functional programming, written in a pure functional style and actually outcompeting successfully these imperative languages that are sort of in their wheelhouse. So hopefully we've now seen a couple different examples of ways that pure functional programming actually can outcompete, outperform imperative at various different tasks. In some cases, like with the rendering in the browser, it's just because pure functional programming happens to be well suited to doing that in a high performance way. In other cases, it's just because of baseline language overhead. It has nothing to do with paradigm, like our Haskell outperforming Ruby at work. And in some cases, it's just through sort of sheer force of optimizations that we're able to say, yeah, even though this task is not innately well suited to pure functional programming, we can make the downside be just that it's less concise and more to read, but not that it's slower. In fact, it can actually still be capable of outperforming other garbage collected languages. And hopefully, now you have an idea of how you actually can outperform imperative with pure functional languages. Thanks very much.